Though mitral valve area by echocardiography can be measured by multiple methods, commonly used ones are two-dimensional planimetry of valve area and pressure half-time methods because of their ease of performance. In two-dimensional planimetry, the valve area is traced out using an electronic caliper and the machine calculates the valve area. Smallest full circle is taken as the mitral valve area, as larger full circles may be proximal measurements of the belly of the mitral leaflets and hence not representative of the actual severity of obstruction. If it is not full circle, it may be a distal measurement or oblique measurement. Mitral valve area by planimetry on echocardiogram is usually obtained from the parasternal short axis view. It can also be obtained from the basal transgastric short axis view by transesophageal echocardiography. The inner edge of the leaflets is traced in mid-diastole. Gain setting should be optimized as high gain settings can underestimate the valve area. Two-dimensional valve area measured in this way gives an overestimate compared to that measured by three-dimensional echocardiography, especially in those with dilated left atrium. This is because better alignment at the tip of the mitral valve can be obtained by transesophageal 3D echo with excellent inter-observer and intra-observer reproducibility. 3D planimetry from the left ventricular aspect is the most accurate method of measurement of mitral valve area. Measurement of mitral valve area after balloon mitral valvotomy follows the same pattern. Measurement using real-time 3D echocardiography is superior to 2D planimetry of mitral valve area in the immediate post-mitral valvotomy period. Real-time 3D echocardiographic valve area has the best correlation with invasively determined mitral valve area in this setting. Assessment of mitral valve area by pressure half-time involves Doppler echocardiography. A pressure half-time of 220 millisecond corresponds to the valve area of 1 square centimeter. Pressure half-time is measured from the descent of the E wave in the transmitral Doppler, usually obtained in apical 4-chamber view. PHT is the time taken for the peak transmitral gradient to fall to half its value. It will also correspond to the time taken for the transmitral velocity to fall by square root of 2, as the pressure gradient is proportional to the square of the velocity. Mitral valve area is equal to 220 by pressure half-time. In this image, green cursor measures the pressure half-time of the mitral stenosis jet. In this case, the pressure half-time was 163 milliseconds and the estimated mitral valve area by pressure half-time was 1.3 square centimeters. Smith and colleagues have shown that both two-dimensional planimetry and pressure half-time methods give good estimate of mitral valve area non-invasively. They found that pressure half-time method is superior to two-dimensional planimetry to assess mitral valve area in those who have undergone mitral commissurotomy. It has been shown that associated aortic regurgitation shortens the transmitral pressure half-time, thereby leading to overestimation of mitral valve area by Doppler echocardiography. An earlier study had shown that mitral regurgitation does not significantly change the estimation of mitral valve area by pressure half-time method. Continuity equation uses mitral and aortic flow as well as cross-sectional area of the left ventricular outflow tract to derive the mitral valve area. The area is measured by planimetry and flow measured by Doppler assessment of velocity time integral. Proximal isovelocity surface area or PISA method utilizes the flow convergence region proximal to the high velocity transmitral jet in diastole. PISA is the surface area of the hemisphere at the aliasing region of the flow convergence. PISA increases as the flow increases and with lower aliasing velocity. To reduce errors in measurement, smaller aliasing velocity must be set to get higher PISA measurement with lower chance for errors. If the flow convergence is not a true hemisphere, the angle subtended by the flow convergence at the orifice must be measured and divided by 180 to get a correction factor. The diastolic flow rate is calculated as follows. Mitral flow is equal to 2 pi r squared into angle alpha divided by 180 into aliasing velocity. R is the maximal radius of the flow convergence region in early diastole measured on the central line of the flow convergence region. V alias, aliasing velocity, alpha by 180, correction factor accounting for the angle alpha between the mitral leaflets. Mitral valve area is then determined by dividing maximal diastolic flow rate by peak continuous wave Doppler velocity of mitral inflow, that is Vmax. PISA method is based on the same principle as the continuity equation. It has been shown to be accurate and reproducible. Proximal flow convergence can be easily visualized. Here are the first set of journal references. Second set of journal references are here. These are the third set of references.